I had prepared to talk on core data, but everyone's been covering that, so I'm going to do this instead. So Swift on Linux, it's the hot new thing that people keep talking about. Next year is going to be the year of Swift on Linux every year. But people are doing some really awesome stuff. I've toyed around with it, and I have a few lessons that I've kind of learned along the way. And since this is really early days, I really want to share with you some tips that I had when I realized that I needed to profile for performance on Linux. So imagine that you've put in all the effort, you've removed all the Objective-C from your code base, you've ported all of your Swift code to run on Linux. So like even things like the type inference that's used in Swift that relies on the Objective-C runtime being available, or a bunch of Darwin-specific stuff that isn't available on Linux. You're pure Swift, and you're so happy. You've just ported your Swift code base to Linux, except that then you realize that it's actually slow. Wait, how could that happen? I thought Linux was web scale. I thought everything was faster on Linux. But there are actually some cases in which your Swift code might be slower on Linux. And there's a variety of reasons why this might be the case. Where things are blazing fast on macOS. Actually, there's quite a bit that's hyper-optimized for macOS. You may not know this, but Swift was kind of designed to run on Apple platforms. And so there's a few reasons that I've encountered why some of your Swift code might actually be slower on Linux. Obviously, there are platform differences, right? From the lowest levels of the operating system, you might have some vast differences in the way that your Swift code is interacting with the OS. So even in low-level libraries, right? If you're dealing with pthreads versus KQ, or using mock ports on Darwin, but then you have to find a different alternative on Linux. Differences in the way that just the standard memory allocators work, right? So some very low-level differences that you don't necessarily think about when you're writing Swift, that you might feel the crunch if you're running this on Linux. You might be using different implementations, right? So think of when you're using Foundation on iOS or Foundation on macOS, it's a different version than if you're using some of those Foundation types on Linux, which uses the corelibs re-implementation, which is the open source version of it. The Objective-C runtime and optimizations you won't have on Linux as well. And oftentimes, these are invisible to you if you're using Swift code. If you're doing things like using the NSString bridged APIs onto String, a lot of that is just kind of transparent on macOS and on Darwin, and you just don't have that on Linux. Okay, so a bunch of reasons why your code might be slower on Linux. It might also be faster, but let's say it's slower for the purposes of this talk. Now, how do you go ahead and identify why that code is slow? You can't use instruments.app, which you'd have on macOS. And instruments.app is an amazing tool for all sorts of profiling. We've seen it mentioned in some of the talks already. But unfortunately, you can't just apt-get install instruments.app. It's a very macOS-specific app. But there are some alternatives. So I want to focus this talk not just on profiling for performance in general, doing things like measuring memory pressure, memory overhead, cache misses, things like that, and really just want to focus on time profiling and CPU profiling. So I have four of the top tools that I want to show off here. There's instruments.app, which would be my suggestion if you need to do any profiling whatsoever. If there's any way, shape, or form that you can restructure the problem so that you can leverage instruments.app on macOS, please do so, because it's an amazing tool, nice GUI, very accurate, powerful, low overhead, really the best of all worlds. But if you're not on macOS, well, then it's not an option. And a lot of what powers instruments.app is this tool called dtrace, which is an extremely powerful scripting and profiling engine. But that's not on all flavors of Linux. It's on macOS, originally written for Solaris. It's on FreeBSD, and there are some ports for like more standard flavors of Linux, like Ubuntu. But most of them don't have what you would need to such as like kernel extensions, to really leverage it. And so you probably won't be able to use this. The next tool is callgrind, which ships with Valgrind, which you might have heard. It basically sets up this virtual machine that proxies all of your application code. Instead of running on bare metal, it'll run that via like a simulator almost that will record each of the low-level operations, and it uses that so that you can profile things. But it's super fickle. Actually, I only got it to work like a handful of times. But one of the advantages is that you can use this from within a container or from within a virtual machine itself, which is super useful if you're just running Docker on your Mac to develop for Linux. And so that's a really useful tool, but super slow, not super accurate. It runs everything single-threaded, and so if your app runs multi-threaded, then you won't really be measuring that side of performance. And then the best tool, if you're using Swift on Linux, I would say is a suite of tools called perf events, sometimes just called perf, which requires running either on bare metal or in a virtualization environment that has virtualization support for hardware counters, which is generally pretty rare. So most of the time, you'll need to run this on bare metal. And this is by far the best tool for profiling things on Linux. It's fast, it's accurate, and you use everything via CLI. And so let's take a step back again and see, okay, well, what are some of the different platforms on which you might want to profile? So you have virtual machines, you have containers like Docker, and then you have running on bare metal on a real machine. And whenever you can, try to run on bare metal, because if you're measuring performance on anything other than that, you'll be essentially measuring the wrong thing, where you're measuring the performance of a virtual machine and not necessarily your code. However, running in VMs and containers is a lot more convenient. So if you don't want to go through the trouble of setting up a bare metal machine, it's often useful just to get like a rough idea by running things in a container, at which point you can use something like callgrind. So you have a few options there. Now, I want to focus the rest of this talk on a specific use case that I actually encountered. So let's dive into a case study for porting SwiftLint to Linux. So for those of you who don't know, SwiftLint is a stylistic and performance linter for Swift code. And so it can find things like conventions that you're not abiding with in your code base, just stylistic, or offer you some performance advice, like use some optimized methods instead of some less optimal code patterns. And a while back, we ported SwiftLint to Linux, and the use case here is that if you want to run this on a server somewhere, so that you don't have to be maintaining a Mac OS continuous integration setup just to do things like comment on your GitHub pull request saying that, oh, maybe you are violating these style guidelines. So there's a lot of good use cases for running tools like this on Linux. So this is kind of what it looks like. It's a command line tool. It lends itself super well for being ported to Linux because it's CLI only. And it basically just walks through all of the Swift code in a directory and then parses that to determine if anything's violating some of the rules. And recently, there was a rule that was added that was particularly slow. And we have all sorts of things to help catch these. We run performance tests as part of danger checks on CI when you're running your GitHub pull request. But this rule in particular, we kind of bypassed, or we just forgot to look at those numbers. And we introduced this, this rule that was actually quite slow. It's a useful rule, but it's disabled by default because it's really just a very specific stylistic choice if you want to separate your let and var declarations. All right, so if you want to group them together for better isolation, for better clarity. And so the first time this rule was implemented, it was super slow. And this is where I actually want to show you what this would look like. So let's go here. All right. So this is SwiftLint, And we'll go ahead and compile what's on the latest master. And this is compiling with Swift 4. And so if we go and run the binary here, you'll notice that there's a few flags that I'm adding. So I'm running Swiftlint's lint command, if you look at the upper right, and then I'm skipping the cache. So Swiftlint caches files that don't change so that it's even faster when you're relinting the same project over and over again. And then there's this other flag called benchmark. And this is some custom profiling that we built into the Swiftlint tool itself that has better knowledge of like the business logic of Swiftlint, so that rather than just profile the whole application, we can actually generate two different files that will show off some of the performance characteristics. And so it generates these two files, and this is just code that we've added. It really just measures dates, like start date, end date, and then saves the milliseconds to these two files, right? So this one breaks it down by rules, and this one breaks it down by file. And so you have the number of seconds on the left side, and then you also have the file on the right. And so most of these files run in just a handful of milliseconds. Some of them run long. But in this case, I want to focus on looking at the rules, and a particular rule that's especially slow. So if we look at the breakdown here, we see a lot of rules that run in like, this is 34 milliseconds, 38. Most of them actually run under 100 milliseconds. But there's a handful that are longer. And then we go from 400 milliseconds to 1,500 milliseconds, so a second and a half. And this is this let var white space rule. And so this one is a major outlier. And in fact, if we go and just go and quickly chart this, right? So we'll put the durations in there. We don't need to see the rules. You'll see that there's this major outlier here. And this is our let var white space rule. Or another way to look at it is that this is all the durations of all of these like 90-some rules that we're running. And then there's this big outlier that takes 20% of the time. And so this is a good thing to go ahead and optimize. And so if you are on Mac OS, the way you would do this, you go ahead and run your app and then attach that to instruments.app. So we'll go and run Swiftlint. We'll go to the CPU profile here, profile and instruments. Let's restart it. Okay. And this is where instruments is just super nice, super useful, super obvious what's happening here, where you have the runtime of this tool, and then you can see kind of what's happening. Here's the main thread, so there's very little, and then we dispatch to a bunch of other GCD threads right away, or GCD queues. But one of the most useful aspects of instruments is it'll show you this heaviest stack trace item here, at which point you can kind of dive in. You can see, well, you start the program, it just starts by the entry point, Swiftlint, dispatches, and then it runs this lint command, visit lintable files. Let's see here. What's happening here doesn't really matter. This is going to be app specific. This gets the style violations for the whole thing. It does a parallel flat map, so running all of the rules in parallel. But this is finding what the heaviest stack trace is. So it's finding the part of your code that's taking the most time. And if we zoom out here, we'll see that let var whitespace is also the part of the code that's taking the most time. And then we can dive in and we can see like what parts of this rule are actually taking the most time. But really all I wanted to show you here was really how nice instruments is, and to give you an idea of kind of how you would do this on Mac OS. So you can do things like click on a symbol and then that'll bring you to Xcode exactly in the point that's causing this. So that's kind of a brief overview of how you would go ahead and do this in Xcode. But if we go back, this is just kind of re-showing what I was showing you. So that's how you do it, but I kind of want you to forget that for a second and imagine that we don't have access to this. Imagine that you're only profiling an issue that's just happening on Linux. So then you could use tools like Docker. If you just run one of the off-the-shelf Swift Docker images, you install tools like Valgrind, for example, which you'll recall Valgrind and callgrind are some of the only profiling tools that you can use in a VM or in a container. So you'll go and build your Swift tool, you'll run Valgrind with callgrind, and then from there you can do a few things. What matters here isn't necessarily these commands. I have them like verbatim in here so that if you're curious about doing this yourself, you can find the presentation and copy paste. But the important part is that you're kind of running this from within Docker. And so it generates things like this dot graph, which you'll notice is a lot harder to parse and a lot harder to understand than everything we were just seeing in instruments. But it's a good idea. It gives you a good impression of kind of the overall execution of your program. But you can see how it quickly gets unwieldy here and difficult to parse. So I actually didn't find any very useful info here. But you can use the same output out of callgrind and open it with a visual editor, something like cachegrind, which will get you this kind of map of where your program is spending all of its time. So again, super useful, but we're not getting very actionable information here. If you notice, it might be hard to read, but most of what's presented here are some of the lowest levels of the stack trace. So things like Swift retain, Swift release that are being called like 12 million times, and that's where most of the program's spending its time. But I'm not going to dive in and optimize Swift retain and Swift release. And just telling me that I should retain less and release less isn't going to help me to optimize my app unless I really dive in. And so these tools aren't super useful, but it can give you an idea of where you're spending your time. So you have retain release, where we're spending a lot of time. We're spending time in libicu, doing things like regular expression matching, doing things like Unicode collation comparison. So this doesn't tell me much other than my software is retaining and releasing a bunch, and I'm using string comparisons a lot. And so short of not having a string parsing program, there's not much that I can do to learn from this. And this is where we go to bare metal. And this is where you start to get a lot more insight using those perf tools that I was mentioning earlier. And so don't pay super close attention to the exact commands here. I'm going to go through them really quickly. But you can go ahead and copy paste this out of the slides if you do want to reproduce this yourself. So starting completely fresh, using DigitalOcean, we can create an Ubuntu image. Go and install a few things like mostly the perf tools that are available on Linux. And this is also kind of finicky, where you need to install the exact version that you need for your distribution, for your Linux kernel version, for your hardware, etc. But assuming that you're running on supported versions, then that should just work. Then we go and download and install Swift. So this is the Swift 4 release. And so we go and install that. We'll download our Swift program and some other utilities like FlameGraph, which we'll use to visualize the performance output. We'll build our Swift program. Now, this is SwiftLint, but this is whatever the Swift program is that you're profiling. And then we run this perf record step, which profiles the application. And unlike callgrind, this will run it exactly how it would run on the bare metal. And it uses a tool called hardware performance counters, which interrupts the CPU and asks it, what work are you doing right now? What work are you doing right now? And so that'll output to a binary file. And then you can use these FlameGraph utilities to generate this SVG. And that's what I want to show you here. So if we generate the SVG, it'll generate this interactive map of where your program is spending all its time. And this is a lot more useful to us. It's not showing the very bottom of the call stacks anymore. It's showing, so starting from the bottom, this is kind of the whole program execution. So it gets to the entry point, SwiftLint. It does some unknown stuff here up front. Don't really care. I think this is mostly dynamic loading resolution. But then we can kind of click into these things and get a better picture of what's happening, right? So this is a GCD call, and then we run our parallel flat map. I'll go and zoom in here. And these are the obfuscated, mangled Swift symbol names. So they're kind of hard to read, but you can kind of see, like, this says parallel map, and then you have get style violations, so you get a much better idea of what your program's actually doing. And then it runs this lint command. And then you can see, if we zoom out, you can see that this here is the lint command, and everything above that is running our 90-some rules that we're applying here. And most of them take about the same amount of time, right? Like, these squares are pretty tiny, except this one, which is our famous let var whitespace rule, right? So that is where most of the time is being spent. And then we can kind of dive in here and see that, let's see where we're spending most of our time. See where it kind of breaks down here, where you have like a few other calls and then this big call. Let's go and copy that. And then we can use utilities like xcrun swift demangle to figure out like what this actually means. So if we copy that and kind of try to break it down here, you'll see that, so let me just break this down. All right, so if we break it down, we can kind of figure out where in the code this is referring to. So we have the module, we have the type. In this case, it's a let var whitespace rule struct. And then this is the method, right? So attribute line numbers is where we're spending most of our time. And it takes an argument of file, and it outputs this set of integers. And so if we go and navigate to that, right, attributes, line, what was it, attribute line numbers, and we look at this code, we can find an optimization. Now, this is very specific. This is basically running a regular expression for a certain string and then matching that with a Swift syntax type. This is how SwiftLint works. And then returning a bunch of line offsets for the matches. But there's an optimization that we can do here. And so if we apply that, if we look at what that optimization is, I've already found it. It's basically just, instead of matching this regular expression, just assume that all of these built-in attributes are what we're looking for. So we can save a bunch of time, and if we run our perf script again, we'll get a very different output. So let's go and compare kind of the before and after. So before, you see that a big chunk of time is being spent here in let var whitespace. But then if we compare with the after, you can see that it kind of disappears. And that's a great thing. It means that we're spending an even amount of time in all of our rules, and that's exactly what we wanted to find. All right, so you can kind of take my word for it that, that this is kind of the output. So again, this is what we found. We found the bottleneck in that big flame graph, like where it actually broke down, and we demangled it. We analyzed kind of where in the source code this was. We looked at the code here and tried to identify if we could find an optimization. So we did this optimization. So it's actually simpler. And if we look at the before and after, you'll see like a drastic difference here. We're spending almost no time in this let var whitespace rule. And that is kind of a very quick world tour of a case study of finding a performance regression on Linux, trying to use different tools to try and identify what's happening here, and performing the optimization, measuring to make sure that it is actually faster, and then shipping it. So hopefully this is useful to your own apps if you're doing something on Linux and you want to identify kind of a performance hotspot, but you don't have instruments.app. There's all of these tools that are available. So check out the slides for the presentation if you'd like to learn more. And then finally, some closing thoughts. First is to embrace kind of app-specific benchmark mode for your code, right? And that's the benchmark flag that we had at the very beginning in Swiftlint. And so you'll find that if you can have benchmark code that can be application-specific, it can really help cut out some of the noise. And so for Swiftlint, it's doing things like measuring the time spent in each file and the time spent in each rule. But for your app, it could be completely different. If you can kind of reorganize your problem so that you can leverage instruments.app, whether that's kind of if you have a foundation mode on Darwin and a core libs foundation mode on Linux, then using the core libs foundation mode on Mac OS, even just temporarily to use instruments, that's always better. Prefer measuring on bare metal over any sort of virtualization because that'll get you much more accurate numbers. Prefer measuring your code in release mode, not debug mode, so that you're actually measuring your app and not just debug useful things that are included. Try to avoid call grind because it's super slow. Like it takes like half an hour to run the same thing that we just ran in like 5 seconds. And then finally, this is kind of throwing it back to you. There's a huge opportunity here to help bridge the worlds between Linux and Mac OS. And a lot of the data that's output out of call grind and out of perf are really hard to parse using these like open source visualization tools. And so there's a huge opportunity there to go and write tools that can convert that data to something that instruments.app would be able to parse and show. That's it. Thank you.
Thank you very much. Thank you, Gilles. Thank you. It actually takes courage to talk about Linux bare metal on stage.
Right. Well, that's why I wanted to do the talk.
Yeah.
That I found very few resources for figuring this out, right? And it turns out that it wasn't all that hard to find. I just had to not think of it as what are the Swift profiling tools on Linux, and just look at more generally what are some of the profiling tools on Linux.
Yeah, and how did you find that? Like, I mean, it's not our world. It's really hard to find those information, I guess, when you.
Yeah, there's this gentleman by the name of Brendan Gregg who has some awesome resources on the perf set of tools, and there is so much more to the set of tools than what I showed off. You can do things like measure memory pressure, do things like identify cache misses for the CPU lines. So there's so much that you can tap into.
Yeah, but as usual on Linux, there are plenty of tools, but hard to put together, right?
Yeah, they're kind of hard to piece together. It's more that it's hard to discover how to piece them together, which is exactly why I wanted to give the talk.
Yeah.
And this was really a whirlwind. Like I went through really quickly a lot of like obscure topics, but I encourage you to check out the slides because there's a bunch of links, and there's like if you copy paste that code, I made sure to have like every single step starting from like spawning a new machine on DigitalOcean, you know, so that way you don't get caught in like, oh, the syntax in the command line isn't working. So hopefully it's useful.
So you spoke about a tooling opportunity, and that reminds me of a talk you did at Altconf about a tooling Swift problem. And since then, lots of things have changed for the better. Thank you to you as well with tools like Swiftlint. And so, so do you think actually, since like Swift on Linux is it's more niche than just Swift on macOS, that this Swift tooling problem can be solved like anytime soon?
That's a great question. And yeah, just for context, that talk at Altconf about fixing the Swift tooling problem was more just saying like, there's so much that's open as part of the Swift ecosystem that we can fix it ourselves as a community. We don't have to wait for Apple to do it. And as for Linux being niche, that's going to be less and less the case. Like this is still very early days for Swift on Linux. And with folks like IBM and Perfect and Vapor folks like all pouring in lots and lots of resources into this, I think it'll be less niche over time. But one thing that I didn't mention is that these some of these tools like valgrind and callgrind are actually useful and provide value beyond the existing tooling built into Xcode as well. It's just kind of a different approach. And so I'd like to see more people kind of using those open source tools, and hopefully that helps solve not just the Linux tooling issue, but tooling issue in general.
Interesting. Yeah, but do you think that at some point we will see developers that will write Swift code for the server, maybe that are maybe only running and using Linux as a primary development machine? That will come?
I think that's still a ways out, right? A lot of
Yeah.
the advantages of using Swift at the moment is that it's the same ecosystem that you used to writing your iOS apps, right? So if you're already using Xcode and you're debugging in macOS, I think it's a lot more likely that Swift on Linux is just one of the targeted platforms of a cross-platform Swift app versus a pure Linux-only kind of tool.
Yeah, it just happened to be cheaper to put Linux servers than macOS servers, right?
That's right.
That's the main.
So I picture a development workflow where you're mostly using Xcode or macOS locally to develop, but then in production you're pushing to Linux, you're pushing to the cloud, to serverless, etc.
Yeah, that can be something realistic, I think. And about bare metal, we're probably some people are not really familiar with the concept of bare metal in the crowd. So maybe you can say a word more about that. And even DigitalOcean is not a provider, a hosting company that we know well. So is it hard to set up?
Right. Well, bare metal just means that you're not running in a virtualized environment. So like the macOS instance that you're running on your MacBook or on your iMac Pro is running on bare metal. And so if you install Linux in a second partition and you dual boot into it, that's also running on bare metal. So it's just a term to mean that you're not running in a virtualization layer. And then DigitalOcean was just like a quick way to have a single command to show how to bootstrap a machine, but you can use whatever provider you want.
Yeah, okay, any provider providing Linux software. And
yeah, there's a specific question actually. So some of the tools you mentioned, of course, just do work on bare metal. But what if you have like a container on a purely Linux instance?
Yeah. So that's a great question, and that's why I showed the tools that do work in a VM and in a container. And some containers also have software virtualization for the hardware features that perf requires. Just the general thing that I would say here is just like you can't really trust numbers when you're profiling even your Swift iOS app in debug mode, you can't really trust performance numbers if you're running in a virtualization environment. Right. But it can often give you a good idea, or at least a starting point that's more convenient than spinning up a bare metal machine.
All right. And you talked a bit about that, but I want to come back on instruments being a really useful and very well thought UI. It's a great tool, but we're just missing this dtrace. Dtrace being the stuff that is inside the app that allows the profiling and providing data to instruments. And so as dtrace is open source, maybe at some point, and already now we have some Ubuntu kernels that are already having some version of dtrace, but will it come in the future and will it be a real solution?
Some people are running dtrace on all sorts of Linux flavors, except that it's a little bit more work, and a lot of times you need to install kernel extensions, and it's definitely behind.
Did you try that?
No, I didn't try that because that's a whole other nest in itself, and I got the data that I needed out of these other tools. But dtrace is incredibly powerful, and instruments.app is also infinitely extensible as well. You can have custom instruments templates that use dtrace scripts to power them, and so even if you're not doing anything on Linux, it's worth learning more about dtrace.
Yeah, we had a talk at one Cocoa Heads a few months ago about dtrace. It was really interesting. And I was wondering if you need to recompile or to have your special kernel, Linux kernel, to integrate dtrace, is it something that you can do in a digital ocean or OVH machine? Can you replace the?
I don't think so. Yeah,
No.
installing kernel extensions in another provider, unless you're like really just renting a metal box that is your machine, you can do whatever you want, like SoftLayer or something like that. Then odds are that they like Linode or DigitalOcean won't be happy if you're installing kernel extensions, I guess.
Yeah, sure. One very important question is, where can we buy your Swifty shirt?
Oh, this is from a Target in San Francisco.
We need to go all the way.
No
Yeah,
target
it's
in
a
France,
high-end
no.
couture boutique. Yeah,
Oh, yeah, you need to just say that. In Le Marais.
yeah, in Bleu Marais.
You are actually working on Swift, on Jazzy, on SwiftLint, on you have a real job at Lyft. I mean, where do you find time for that? You're even a father, I think.
The latest release is a 3-month-old boy. Thanks. Who's currently just kind of touring Paris. So yeah, we're having a blast. And the trick is to just want to push the boundaries and like toy around in things that people haven't really done before, even if they're not terribly useful as you're doing them. Because following a tutorial is immensely useful as a learning tool, but ultimately to kind of extend your own comfort zone, it's nice to try to do, and often fail, but to try and do things that haven't been well documented and haven't really been done, like reverse engineering things. And
so building to learn. That's what you do. You build things to actually learn.
yeah, and it's a ton of poking around and not really knowing what you're doing. And I still like have a very cursory knowledge of all of these tools, and I'm sure I got a bunch of things wrong. And probably like a handful of people watching this are just gonna shake their head and say someone is wrong on the internet. But it's part of learning.
Awesome. And anyway, thank you for this talk, and thank you for all the tools that you're providing to the community. Thank you.
Thanks for having me.
Okay.